Unit 1 kinematics is the study of either accelerating or not accelerating objects. We start Unit 1 with the DST triangle. D for distance, S for speed, and T for time. DST triangle involved in situations in which there is no acceleration. If there's no acceleration, you get to use this triangle to solve for stuff. And this is our first unit that we'll explore. And you'll be surprised at how often you use this DST triangle. In fact, you're going to get in situations probably where you're reaching for a kinematic or more advanced equation, and this equation is the only one that is necessary. In addition to the DST triangle, we use the big four kinematic equations here. These four equations relate to the motion of an object that is experiencing acceleration. Variables involved in the big four kinematic equations include initial velocity of an object, final velocity of an object, acceleration of an object, the time of the motion described, and the distance covered by the motion described. The big four kinematic equations follow. Boom, there they are. The one that's not given, well, three of these are given as part of your equations list come the AP exam. This one is not given. The reason for that is that this equation relates to situations in which you're experiencing a steady acceleration. So if you have an increasing acceleration value, that particular equation does not work. And a good chunk of this unit is, as you'd expect, questions that outline, variables. You pick the three variables from the problem and then plug into the appropriate kinematic equation to solve for whatever fourth variable that you intend to solve for. That's when, we could use that phrase plug and chug to describe what to do in physics. In addition to the big four, we have graph interpretations to cover in Unit 1. That is to say, looking at position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. And making sure that these three graphs are tethered to one another and that what influences one graph influences the other graph. We'll work out a lot of problems like this so that way you can build familiarity with this topic in class. But basically, if you have a steady acceleration, let's say in your beginning, your motion from distance equal to 0 meters, if your acceleration is steady, your velocity would be increasing steadily. And then position is doing that exponential graph like so. A good chunk of this unit is either interpreting or generating graphs to accurately describe motion. Another quick example, if you have a steady velocity and your distance begins at 0 meters, what is your acceleration and position versus time graphs doing? Well, acceleration would be 0 since you're not accelerating. And if you begin your distance from 0 meters, your position versus time graph would look like this, steadily increasing. Finally, yet another quick example, if your velocity value begins high, and you begin your distance from 0 meters, and maybe perhaps it creeps down to then go negative. If you begin your distance versus time graph and beginning at a distance of 0 meters, what would that look like? Well, correlating with the high velocity value, you'd have a steep slope right off the bat. But then it would kind of taper off and go into 0, correlating really specifically this brief horizontal line with velocity equal to 0 over here. Your acceleration would be a constant negative for that whole line, creeping that position versus time graph back down. Finally, Unit 1 ends with our two individuals, A and B, relative motion problems. Let's say that we have two individuals. A is running at a velocity and is trying to catch up with individual B running the same direction. So both of these individuals are moving the same direction. How would you find, this is, the classical train problem, how would you find the time and distance from position equal to 0, considering this, position equal to 0 meters? How would you find the distance to the right of 0 meters in which individual A catches up with individual B? How would you find the time in which individual A catches up with individual B? What you do in order to answer questions like this is you build distance graphs or versions of the DST triangle as they relate to each individual. So individuals A's equation, distance equals velocity times time, is a very generic derivation of the DST triangle. Individual B's equation is a little tricked up. For one thing, they each have their own individual velocities. We're assuming that individual A is a higher velocity since individual A will catch up with B. In addition, individual B has a distance tacked on to his DST triangle, this distance being the distance of the head start with which he receives. You set these two equations equal to one another and essentially solve for t, as shown here. Now simply solve for time. In this case, the workup would look like this. And then once you have your time value, you can replug it back into either equation to solve for the distance traveled. In fact, that's a good way to check your answer. Whatever you received for this time value here, plug it back into this original equation, solve for d, plug it back into this original equation, solve for d, the distance traveled. And that's a great way to figure out what your time is at which the two individuals meet and what the distance is at which the two individuals meet.